we go. So the first thing, just like with all the other Zoom meetings that we have and that we're gonna do, I'm recording this one as of right now. And once we are done for today, I'm gonna post it in the September 22nd chemical bonding section under Zoom meeting recordings. So if you ever want to go back and watch me go through the notes that we're about to talk about again, you just go to the classwork tab on the Google Classroom, and right under Zoom meeting recordings, you can just scroll down to the notes that you want to look over. Specifically today, we're going to be talking about chemical bonding. Speaking of that, the notes for that are right down here, Tuesday notes, chemical bonding. And so one thing that I wanted to bring up, and that people with really good eyesight might have noticed, is that this week, since we're halfway through the term so far, we are going to be having our midterm exam this week. So the first test in IPC class. Because we're doing this online, it might look a little bit different than some of the exams that you've taken in person in class before. So for one, the exam is going to be posted tomorrow. So Wednesday morning, the exam will go live, but as I've labeled on here, it is not due until Friday. All right, it's a little bit longer than some of the work that we've been doing so far, and it covers everything that we've talked about, all the way back to the solids, liquids, and gases, the properties and changes of chemicals, the atoms and electrons and protons, and the electron shells, all of that stuff, plus some of the stuff that we're going to talk about this week with the chemical bonding and the mixtures and compounds stuff we'll talk about on Thursday. That stuff is going to be on the exam as well. So that's why I'm making sure that the exam isn't due until Friday, so that you guys have a couple days to think about it, work on it, leave questions and come back to them later if you need to. Stuff like that. Just like with all of our other worksheets and assignments and stuff that you guys have been doing, there's two different ways that you can complete the exam. You can go onto the Google Doc version and go through, take it kind of like a regular exam. So for the multiple choice questions, you can write down your answer or like highlight which answer you like the best. There's some fill in the blank type questions. There's some short answer type questions where you have to write out your answer in like 2 to 3 sentences. Oh, whoops, I have to go in and fix this. It's a little bit messed up. Anyways, there's going to be some stuff working with those atoms that we've been talking about for the last couple days. And so it's only 20 questions, but it covers everything that we've been going over in class so far. So that's the Google Doc version. There's also the Google Form version, which looks just a little bit different than the Google Forms that you guys have done so far, mostly just because it's going to be in sections so that you're not having to constantly scroll down a whole big online web page. So for the first section, you just have to write in your name and then hit next. And then the next section, just like with the Google Doc version, has multiple choice questions, fill in the blank questions where you just put your answer underneath. Some answers based on a diagram, stuff like that. So that is what is kind of the big thing that's a little bit different coming up later this week. So this is on top of the regular daily assignments that you guys are doing for attendance or for grades. But I've made those daily assignments super short and easy this week, so that they're not too much of a distraction from getting through the IPC exam. Again, this exam will go live tomorrow morning, Wednesday morning. But unlike the other daily assignments and stuff that we've been doing in here so far, it is not due until the end of the day on Friday. So you have all day Wednesday, Thursday, and Friday to work on it and turn it in. All right, any questions about the midterm that's coming up for this week?
Is that all that we have to do for the assignment for this week?
No. So in addition to the midterm, there's also going to be those short little daily assignments. This week, I've made them extra short so that they take up less time, so you can spend more time on the midterm.
Okay.
I had the question today about the electrons, and then there's going to be an assignment for the notes that we're talking about today, another question on Wednesday, and then 2 assignments for Thursday and Friday. But again, I try to make these like other daily assignments, 2 or 3 questions each, so that they're nice and short for you guys. They are still due and they are still for a grade, so make sure that you get them done, especially on Wednesday and Friday, so that it counts for your attendance. But like I said, hopefully they shouldn't take up too much of your time. I think yesterday's assignment was 1 question. Today's assignment is, I think, like 4 questions. Wednesday's assignment is 1 question. Thursday's assignment is 2 questions, and Friday's assignment is like 3 questions. All right. So did that answer your question, Dasani? Any other questions you got?
I was about to say what I was about to say. Okay, so going through because it may not seem like I be going through the work or whatever. I'll be looking at the work, but I'll be like, is this what I'm supposed to do? I don't select it. Like I don't select it or select it or to send it back. I don't send it to nobody. Like I'll be looking at it, but I don't send it back to y'all. Like I don't probably finish it either, but I'll be looking at it and I'll go through it in my head. But for some reason, I don't send it back to y'all to see like my work or whatever. Cause I barely be doing the work. I just be looking at it in my head or whatever. Like when y'all send them, cause I go through it all the time. Like every day I'm going through the classroom or whatever, just looking through all my classes. And I'm doing it in my head, but I'm not doing it on the phone. It's hard for me to send it back. Like I don't know how I be doing that, but that's why I really be messing up at is sending it back to you guys. That's the only thing that I be messing up on is sending it back. Like Samantha.
Hold on, I think you got yourself muted accidentally.
My bad, but I don't know. My bad, sorry. But yeah.
No, that's no worries. So that's all right if you haven't been sending stuff back in so far, but definitely do, when you get a chance, go back and work on those and send them in, because that's what we're taking as your grades for this, is all of those little Google Classroom assignments. And so if you don't turn any of them in, then I'm going to be like, oh, well, Honey hasn't done any work so far. Yeah. So that's going to be a 0.
Yeah, that's understandable too. I'm sorry. My bad. I will. I'm trying.
That's no worries. And the other thing too is that you've done a couple of these already, I think, but
I'm gonna have to keep going through them because I can't remember. Like I don't know. I need a passing grade. I don't need no just I did it. I need a passing grade.
Exactly. So if you want, you can always reach out to me and ask me like, hey, Mr. Stanley, which assignments have I not turned into yet? And
I can't send an email back as I'm doing it. I don't be doing that though. I be like, I don't know if I can do that right now. And I'll be working like sometimes like at 12 at night p.m. if I'm not ain't nothing else to do. Or if I'm up like at 1 o'clock in the morning, no, I ain't got school at that time right now. I'd be like, let me go through this classroom and see if I can work through my work. And I do, but I just be like, I ain't never sending nothing in. I'm like, well, sometimes, but not all of it. I don't feel like I'm filling in all the questions, is what I'm saying. Like the answers, not questions, but answers.
Right. So the nice thing about the Google Classroom is that if you use so I'm posting all the assignments in like 2 different versions.
Yeah. Yeah.
Google Doc, which is like the normal kind of worksheet version, but there's also the Google Form, which is like an online web-based version. So if you do the Google Form, then as you go through, all you have to do is...
It's somewhat like something like that, but I did not submit it like all the way through, so I don't know if I'm like doing all the work that I'm supposed to be doing. I didn't answer, like, I was guessing on some of them. I ain't gonna lie.
That's all right. That's all right.
I was like,
As long as you get it turned in is the main thing. So once you go through it all, and at least if you got all the questions answered, and then just hit submit.
Yes, that's the button.
Send me a notification on my computer. Let me know, like, hey, Dasani just turned in this worksheet, this form.
Okay. Okay.
And so that way it's easy for me to also keep track of when you're getting stuff.
Hey, girl, don't be making that big old mess over there. Don't do that. Don't do that.
All right.
Mr. Stanley?
Yes, ma'am.
I had just turned in that sheet from the 17th, and then it showed me the work that I sent in, and it was blank again. Can you, after the class, will you check to see if it's still blank? Because I definitely filled it out.
Yeah, can do.
Thank you.
All righty. Good questions there. All right, so for today, we're going to jump into a concept called chemical bonding. So this idea of we've got all these atoms that we've been talking about, and they've got all their little electrons swirling all around them. But how do those electrons actually get those atoms to stick together? How do we get atoms to form into new chemicals, new compounds by doing stuff with their electrons? That is what we are going to jump into for today. All right, let me make sure I'm still, yep, looks good. All right, so today we're talking about bonds. We're not talking about this kind of bond. We're not talking about this bond either, even though he's a great bond. We're talking about chemical bonds, not James bonds. So chemical bonds are essentially how atoms stick together, how different atoms, or sometimes the same atoms, stick to one another. There's 2 major types of chemical bonds that we're going to be focusing about and talking about today, but they both have to do with electrons, those tiny little negative particles that are zooming all around the outside of atoms. So we've been talking about atoms the last couple of weeks, how they're the building blocks for all the other matter in the universe, all the other stuff in the universe. We've got our protons and neutrons hanging out in the nucleus in the middle right here. And then we've got electrons on these shells. And we spent a lot of time last week talking about these electron shells. So this is helium. Helium is atom number 2 on the table. So he has 2 protons and 2 electrons. You may remember that our first electron shell can hold 2 electrons. So helium has a full first shell of electrons. He's got 2 out of 2 electrons on that first shell. So last week we were talking about how we can figure out how many electrons an atom is supposed to have based on its atomic number. Like I was just saying, helium has an atomic number of 2, so it has 2 protons and 2 electrons. And those electrons don't just zoom all over the place around our atoms, around our nuclei of the atoms, right? Instead, they orbit around the atom in these shells. So they are constantly moving, but they're constantly moving in a set area, either really close into the atom on that first shell, or a little bit further away on the second shell, or even further away on the third shell. So these electron shells are important because however many electrons are on the outside shell of an atom, that is going to determine how that atom reacts when it comes into contact with other atoms. So we talked about reactivity the other week when we went over the shells and the different metals and nonmetals. And we talked about how electrons can be really reactive with other atoms based on kind of their electron number on their outer shell. And so today we're going to look at a couple of examples of how exactly that works. So hopefully you guys are pretty familiar with our electron shell rules at this point. Shell number 1 can only hold 2 electrons, but the rest of them, number 2 and number 3 that we're going to focus on in this class, they can hold up to 8 electrons. So 2 on the first shell, 8 on the second shell, and 8 on the third shell. So since the electrons on the outside shell of an atom either going to be like the second shell if we're talking about an atom with not that many electrons, or the third shell if we're talking about an atom with lots of electrons, they're super important. So they are called valence electrons. They get their own fancy special name. So valence electrons are the guys that are on the outermost shell of our atom. All right, Dasani, you got a question?
Are we adding, subtracting, or multiplying? Or are we dividing it, like with these electrons? Like, because I know they're like kind of like I know they're chemicals, but I'm saying like chemicals is adding, subtracting, and dividing too. So I'm trying to figure out like what kind of electrons are we doing.
So when we're talking about the electrons that are on a single atom, we're always going to be adding them, right? Well, if we're trying to figure out shells,
okay.
right? So we have 2 electrons, we can add, or if we have an atom that has 3 electrons, we can add 2 of them to the first shell, and then the leftover one goes on the third shell. So that's for each individual atom. We add electrons to figure out how they fill up the shells. When the atoms are interacting with one another, then it's going to be a little bit different. And we're going to talk about what they do with their electrons when they interact. All right, good question, good foreshadowing. So valence electrons, very important idea for today. These are our outermost electron shell. So like lithium is a super simple atom. Lithium, like the stuff in batteries, is atom number 3. It has 3 electrons. So lithium has 2 on the first shell and 1 on the second shell. So lithium has 1 valence electron because his outer shell is the second shell and he's only got 1 electron on the second shell. So it doesn't matter if it's the second shell or the third shell, whatever is the most outside shell for an atom, that determines the valence electrons that atom has. So here are some different atoms. We have hydrogen, which is our most basic atom. He's got atomic number of 1. So he's got 1 electron on his first shell. So on these pictures, you'll see filled in dots for the electrons. And then the little blank circles are the amount of spaces remaining on the electron shell. So for example, carbon, we talked about him the other week. He has an atomic number of 6. So he's got 6 protons and 6 electrons. We've got 1, 2 on the first shell, and then 1, 2, 3, 4 on the second shell. So 6 electrons total, but because there's only 4 electrons on carbon's second shell, that means he's got 4 openings essentially, right? On his outer shell, carbon's only got 4 out of the 8 outer shell electrons. Nitrogen, 1 electron higher than carbon. So he has 5 valence electrons on the outer shell here out of the 8 total possible. Oxygen, even higher, 1 more electron. So oxygen has 6 valence electrons, and out of the 8 possible total for that shell. So one kind of new thing about atoms that we're going to go over is this idea of something called the octet rule. And the octet rule says that atoms tend to either gain, lose, or share electrons so that they can have 8 electrons in their outer shell. So in a little bit, we're going to talk about how exactly they can gain, lose, or share electrons. That has to do with the chemical bonding that we're going to go over. So just based on this, we said that carbon only has 4 out of the total 8 electrons on its outer shell. So carbon wants to gain 4 more electrons. In order for this shell to be full, carbon would have to get 4 more electrons on there somehow. Similar with nitrogen, he's already got 5 electrons on his outer shell. So if nitrogen was able to gain 3 more electrons, then it could have that full set of 8. Same thing with oxygen. Oxygen wants to gain 2 more electrons, right? It has 2 open spaces on its outer second shell. So if oxygen could somehow gain 2 more electrons, then it would have a full outer shell and it would satisfy the octet rule. So these valence electrons, these sort of outside ring electrons, can determine what types of bonds that our atoms are going to make. And it's all based on how many they need in order to get up to 8 electrons. So like I said, in a little bit, we'll talk about how they can gain or share or lose these electrons to have that full outer shell. But remember, we're always trying to get back to 8. And so however many valence electrons we have, we're going to either add some more in or get rid of some in order so that we can get a nice full outer shell, whatever that might be. All right, any questions so far on electron shells, valence electrons, octet rule, anything like that? All righty then. So here we have some more pictures of atoms. So here's the guys that we were just looking at. We've got carbon with the 4 outer shell, nitrogen with the 5 outer shell, oxygen with the 6 outer shell. We've also got some guys like fluorine over here, who has a 7 outer shell. So he's really close to gaining that 1 more electron to have 8. But we also have some guys like beryllium, who has only a 2 outer shell, and a lithium, which has only 1 outer shell. So while these guys might want to try to gain a couple more electrons in order to have that full second shell, these guys over here are going to be a little bit more likely to lose 1 or 2 electrons so that they can have a full, in this case, first shell, right? Because what's easier to do? Gain 7 electrons or lose 1? In these guys' cases, it's a lot easier to just lose 1 or 2 electrons compared to these guys over here that are trying to gain just 1 or 2. You'll find the same pattern just on the third shell in our atoms down here on the third row of our periodic table. So like carbon has 4 valence electrons on his second shell. Silicon has a full second shell, but it has 4 valence electrons on its third shell. Same thing with phosphorus, just like nitrogen. He's got 5 valence electrons on his third shell. And sulfur and chlorine are the same as oxygen and fluorine. We've got 6 and 7 electrons on the outer third shell. Now, some elements that don't have any problem with gaining or losing electrons are these guys over here, neon and argon, to name just a few. You'll notice neon has a completely full second shell, and argon has a completely full third shell. So these guys do not want to gain or lose any electrons whatsoever. They don't want to do any sort of reactions with any of these elements over here. You may remember from yesterday, or from the other day, we were talking about how these guys over here are called noble gases. That's because they have a full second or a full third shell, so they don't want to interact or mingle with any of these other elements over here. They're good just being the way they are. They've got their full outer shell. They are happy as a clam. So here's another way that we can show the valence electrons of some different atoms. So this gets rid of all of the interior electrons, the ones on those full inner shells, because those ones don't really play a part in the types of bonding that we're going to talk about in a little bit. Instead, these electron dot structures just show the valence shell electrons. So this way, it's really easy to see how similar these atoms in these columns are. So like we mentioned earlier, carbon has 4 valence electrons, so he gets 4 little dots around the carbon. And silicon has 4 valence electrons, so he gets 4 little dots around him. Nitrogen has 5 valence electrons, so nitrogen's got 5 dots. Phosphorus also has 5 valence electrons, so phosphorus gets 5 dots. And so on and so on and so on, down to fluorine and chlorine with 7 dots for their 7 valence electrons, and neon and argon with 1, 2, 3, 4, 5, 6, 7, 8 electrons, showing their completely full outer shells. I mostly just want to show these to you guys because they may come up in later sets of notes, and so I want you to know what those structures are showing if we see them again. All right, so main topic. So all of that was kind of gearing up for the main topic of today, which is chemical bonds. How atoms and chemicals bond and stick to each other. And it all has to do with trying to fill up their electron shells. So there's two major ones that we're going to talk about today: ionic bonds and covalent bonds. So these are the most important ones, so pay the most attention to these. Metallic bonds we'll talk about a little bit because they also exist, but they're not as important to us as these first two. So ionic bonds we're going to talk about transferring electrons, taking an electron from one atom to another. Covalent bonds is where the atoms are sharing electrons between them. They're both holding on to sets of electrons. And then in metallic bonds, the last thing we're going to talk about, we have this kind of cool electron cloud that forms. We'll worry about that when we get there. All right, so up first, number one, ionic bonds. A bond formed between two atoms or two ions, and we'll talk about what that means in a second, by transferring electrons. Taking an electron from one atom and giving it away to another one causes those two atoms to become closely attracted to each other. So in general, it's whenever we have metals and nonmetals that are interacting with each other. So we've got one metal and one nonmetal interacting. That tends to form an ionic bond. Don't worry about electronegativity. That's not really something we're going to go over. We're forming these bonds by transferring electrons. We're moving electrons from one structure to another structure. From one valence shell of an atom to the other valence shell. Don't worry about the second part about the conductors and the melting point, but when we move these electrons, we produce new charges in our atoms because this electron was negative and we're taking it away from one atom and giving it to one atom. So we're making one atom less negative when we take that electron away. And we're making the other atom more negative when we give it that electron. And we'll look at the kind of repercussions of that in a second. But again, major thing to focus on with ionic bonds, transferring electrons, completely moving an electron from one atom to another. So talking about it in words is all well and good, but if you really kind of want to get and understand what this is talking about, pictures I find help way more. So here we have a sodium atom. So sodium is Na, and a chlorine atom. Chlorine is Cl. Chlorine has 7 valence shell electrons. So that's what the red dots. I would stop this animation if I could, but unfortunately I cannot. It just kind of keeps going on its own. So that's why I'm talking even while it's moving around. Chlorine is a 7 valence electron atom. He's way over there on the right-hand side of the table. And so that's what these 7 red dots represent around chlorine. So chlorine really, really, really wants one more electron so that he can have 8 electrons around his shell. Sodium only has the 1 electron on its 3rd shell. So he has a full 1st and 2nd shell, but just the 1, in this case, it's a little yellow electron on the 3rd shell. So sodium wants to give away that electron in order to have a nice full 2nd shell be his outermost shell. So chlorine is really looking to take in 1 electron. Sodium is really looking to give away 1 electron. So that is exactly what they do. The sodium atom gives its electron to the chlorine atom. But like I mentioned, this causes the charges on the atoms to change a little bit. Sodium just gave away his electron. He doesn't have that last electron anymore. And electrons are negatively charged. So that's why sodium gets a little more positive, because the electron, the negative went away, so now it's a little bit more positive. On the other hand, the chlorine just accepted an electron. The chlorine just picked up an extra negative charge. So when the chlorine gets that electron, it becomes a little bit more negative. So that's why you see this positive and this negative forming up on these atoms. Now, you may have heard the phrase opposites attract before when people were talking about like relationships that their friends are in. And well, maybe that kind of works, kind of not in the human world. And the atomic world, opposites definitely attract. Positive and negative charged atoms are going to be attracted to each other. So this is how ionic bonds are formed. One atom gives away electrons, the other atom accepts electrons, and then the positive and the negative atoms are attracted and stick close to each other. They kind of work like magnets, right? In magnets, you have a positive and a negative magnetic field that are attracted. In atoms, it's positive and negative charges that are attracted. So it gives away the electron. We get a little bit more positive, a little bit more negative, and then they're attracted to each other. If you want to think about it in terms of like kind of picturing it in your mind, imagine that the one electron, in this case, the chlorine, is kind of like one big greedy dog, right? It has 7 electrons, but it wants one more electron really, really bad so it can have 8 on its outer shell. So it takes away an electron from this smaller guy, this little sodium dog over here. But the sodium dog is going to hang around the chlorine dog because maybe he'll get that bone back someday. So if that works to kind of help you think about it, then all the more power to you. We have one atom or one dog that's taken up all of the electrons, one atom that is giving away the electrons, and after they make that transfer, they then stick together. All right, so here's another not quite as moving picture to kind of show you what's going on. Again, sodium, full first shell, full second shell, just has that one little guy hanging out on the third shell. Chlorine, full first and second shell, but just has that one space open up on the third shell. So sodium gives his electron away. So now there is no more third shell for sodium, right? He's got 0 electrons on that third shell. So he's got a full second shell, which makes sodium happy. Chlorine was able to add that electron to his collection. So now chlorine has a full third shell, which makes chlorine happy. And then because sodium is now positive and chlorine is now negative, those opposite charges attract each other, and now they've become one chemical, one compound. They've turned into sodium chloride, NaCl, also known as table salt. So table salt, like the stuff that you use in your food, is sodium chloride. Sodium and chlorine atoms that have given away or taken up all the electrons and so are now just sticking together in little salt molecules. So when you get lots and lots and lots of sodium chloride atoms together, when they do stick together, they'll form up into these crystals, which will then bunch together in order to make these big blocks of salt, which are the tiny little flakes that you sprinkle on your food. All right, I like to start off with this one because it's a little bit trickier than the other type of bonding, so I like to make sure to get to it first. Any questions about ionic bonding? What's going on when we're giving away or accepting electrons and then have these positives and negatives going on? Any ionic bond questions so far? All right, nice. Seems like you guys are pretty okay with that one. So next type of bonding is a little bit different. It's a covalent bond. And so this is where we are sharing our electrons. So it's covalent because our valence electrons, those outer shell ones, are being shared by multiple atoms. So they're co-sharing these electrons with each other. So we're not giving away and taking anymore. Now we're being nice and sharing. So in general, covalent bonds tend to happen between nonmetals. So before, with the ionic bonds, that was mostly metals and nonmetals together. Covalent bonds are when we have mainly nonmetals together. Again, we're sharing pairs of electrons. And so we have one or more elements that instead of taking an electron in order to make their outer shells full, they're both using the same electron in each one of their outer shells. They're sharing that electron. Blah, blah, blah. Don't really have to worry about that third point there. So you've probably heard of a lot of elements that are covalently bonded before without even knowing about it. Things like H2O, or water, is one oxygen element, atom, covalently bonded to two hydrogen atoms. CO2, carbon dioxide, the stuff that we breathe out of our lungs or comes out of our cars or out of power plants, that's one carbon atom, covalently bonded to two oxygen atoms. There's also things like propane, which is C2H6, two carbon atoms bonded to 6 hydrogen atoms. So how do these covalent bonds work? What is going on to have this sharing going on? A super simple example might look something like this. So this is CH4, 1 carbon, 4 hydrogen atoms. And if you remember from our earlier examples, carbon only has 4 electrons on his outer ring. So these blue electrons right here, 1, 2, 3, 4, those all originally belonged to carbon. So carbon only has 4 out of the 8 valence electrons, and so he wants 4 more electrons. So along comes hydrogen. Hydrogen only has 1 electron on its first shell. So hydrogen really wants 1 more electron in order to get a full first shell of 2 electrons. So in the case of CH4, we have 4 carbon electrons in blue, and each carbon electron is shared with a hydrogen, which shares his electron with carbon. So this bond over here, this hydrogen is bonded with 1 carbon electron and 1 hydrogen electron. So he feels like he has 2 electrons on his first shell, so he's happy. That is a full first shell. Same thing with this hydrogen. He shares his electron with carbon. Carbon shares its electron with hydrogen. He feels like he's got a full first shell, so he's happy. Same thing with hydrogens number 3 and 4. Each one of these hydrogens is sharing their outer electron with their 1 single electron with carbon. And so carbon is sharing each one of its 4 valence electrons with hydrogen. So now each one of these hydrogens has a full first shell, so they're happy. And this carbon, because it's got 4 electrons from the 4 hydrogens, it's filled its second shell. So carbon is happy. Again, we didn't take away an electron from hydrogen or take it away from carbon. Instead, they are sharing. They're both using the electrons to fill up their outer shells. So here's what it might look like in a little bit more action. We have these 2 different atoms. Each one has 7 electrons around the shell. Again, if I could pause it for a second, I would, but it's got a mind of its own, so it's just going to go. So they both have 1 electron missing from their outer shell, right? This guy's got 7 out of 8, and this guy's got 7 out of 8. So if they each share 1 electron with each other, then they both feel like they have 8 electrons, right? Because atom 1 has 7 electrons plus the 1 from atom 2, so he feels like he has 8 and is happy. Atom 2 has 7 of his own electrons plus the 1 from atom 1, so he feels like he's got 8 and so he's happy. So this is what we mean when we talk about sharing the electrons in covalent bonds. We're not giving them away, we're not taking away or accepting any electrons. Instead, both atoms, or in the case of this guy, multiple atoms, are sharing their electrons so that everybody can feel like they have a full outer shell. Any questions on covalent bonding so far? A little bit simpler than ionic bonding, but anybody have any questions or have anything that they want me to go back over again? All right, doesn't sound like it. So we'll wrap up by talking about really quickly this last thing, metallic bonds. Again, we're not really going to focus on them too much. I just wanted to bring them up because whereas the other 2 bonds, remember the ionic tended to be metal and non-metal together, and the covalent tended to be 2 non-metals together. Metallic bonds tend to occur when we have 2 metals or maybe lots of metals together. So instead of sharing and giving away or taking electrons, instead when metals get together and kind of get aligned with each other, electrons form this kind of cool cloud structure around the atoms. So the electrons just are all kind of constantly flowing around all the different atoms. So this is what gives metals some of their cool properties, like their shininess and their conductivity, is due to all of this kind of sea or this cloud of electrons all moving around. So it's like all of the different metals have plenty of bones to go around, so they're all happy. They all feel like they have enough electrons for all of their shells. Again, the metallic bonds, don't worry about too much, don't focus on too much. I just wanted to bring them up as kind of like the 3rd type. But the main thing to take away from today is our ionic bonds and our covalent bonds. So taking away an electron from one atom and giving it to another, and then those different charges causing an attraction in the ionic bond, or atoms sharing electrons and so being like physically stuck together by sharing their electrons and creating those covalent bonds. All right. Any final questions on ionic bonds, covalent bonds, valence electrons, any of that good stuff that we've went over so far today?
I have a question, Mrs. Penny. You had said something like at the beginning of the class, like atoms that take have less and atoms that give have more, or what did you say something about that? I'm just trying to write it down so I can understand the word for today.
So, actually, hold on. Forgot to restart my screen. There we go. So I was referring to their charges, essentially, where when an atom takes an electron, like this chlorine is going to do, last week we talked about how electrons are negatively charged, right? They're a minus charge. So when an atom takes an electron, it gets more negative, more minus. And then because that electron left the other atom, he got more positive, right? There's less minus, less negative on the sodium now, so he's more positive. There's more negative on the chlorine than there was before, so he's more negative.
Okay.
All right, good question. All right, so the final thing that I wanted to show you guys today was the homework that goes with this set of notes and with the discussion that we've had today. Again, I made it super simple for you guys so that if you get behind on this, it's not too hard to get caught up before the midterm. All it is a couple of pictures of different types of bonds with some questions about what is being displayed there. So the homework has pictures of bonds going on, and it's asking for each picture, I want to know what type of bond is being pictured here and how can you tell? So what is it about this diagram that tells you that this is definitely covalent bonding or this is definitely ionic bonding? So we have one picture, one diagram that looks like this, and one diagram that looks like this. So again, for each one, I want to know, is this a covalent or ionic bond? And how can you tell? What in it is suggesting to you that it's one of those types of bonds? All right, so that's the assignment that went live today. So again, since you guys are awesome and you came to the Zoom class, you've already got your attendance for today, but make sure you get back to this assignment soon so that you can turn it in for a grade. And as always, if you want to go back and look at the notes that we just talked about, they're right here in the 922 Tuesday notes section on chemical bonding. And then once we are finished for today and the video is done uploading and being processed, I'll post a video of me going over the notes in the chemical bonding section under the meeting recordings area up here. All right. Any final questions about atoms, electrons, bonds, or about the midterm that is coming up?
When is the midterm?
So the midterm is going to go live tomorrow morning, but it's not due until Friday. So you have the next 3 days to look on it, kind of work on it at your own pace, answer the questions as you have the time to, and then you don't have to turn it in until the end of the day on Friday. So all of the stuff that we've been talking about in class so far, going all the way back to protons and neutrons and the liquids and gases and solids and stuff like that.
Okay.